Good morning, everyone. Thank you for joining us, or good afternoon, depending on where in the country you are located. My name is Nick Friend. I'm the Director of Marketing for Upsite Technologies, and I will moderate today's webinar. Thank you so much for attending. We are Upsite Technologies. If you are unfamiliar with us, we are considered the pioneers of data center airflow management. We were started by Ken Brill back in 2001, and Ken Brill, as you may know, also started the Uptime Institute. So we have deep roots in airflow management science and history, and we're pleased to share that level of knowledge with you today. You may also know us by our products. Our first product was the Cold Lock Integral Grommet, which essentially started airflow management in data centers back in the early 2000s. Since then, we've also launched our line of hot lock blanking panels, aisle lock modular containment, and energy lock monitoring. So today, we are glad you joined us because we've declared June as Airflow Management Awareness Month. What we are seeing in the industry is that there's still a lot of issues around this topic that exist and a lot of misinformation. So this month, we've declared a series of webinars to help correct a lot of that misinformation and really help educate and empower managers and operators of data centers. So with that being said, today's topic, we're going to talk about how IT decisions impact facilities, the importance of mutual understanding. This topic is based off of a white paper that we published late last year, authored by Seaton and edited by Lars. So those are the two speakers today that I'm going to briefly introduce you to. Lars is the Senior Engineer and Company Science Officer of Upsite. You may be familiar with him from industry events all over the world. He regularly authors topics in this space and presents at several events every year. And Lars today will be joined by Seaton, who I mentioned is the author of that white paper that shares a similar title. As you probably know, is an industry heavyweight. Has been around for quite a while, about 30 years, and served for many of those years at Chatsworth Products, where he authored numerous white papers and led many discussions on the topics we're going to talk about today. We're thrilled to have Ian as a technical advisor to Upsite, and we're glad to have him join us today. So with that being said, we'll go ahead and get started, and I will hand it off to Lars.
Thank you very much, Nick. Well, I'm really happy to be doing this webinar, speaking on this content, because in my history in the industry, I've bumped into this issue on numerous occasions. I spend most of my time talking about technical issues and fluid mechanics and thermodynamics and heat transfer and all those sorts of things, but it always comes around to some sort of relationship or organizational structure dynamic that is hindering what's happening in the data center. You know, I've had conversations with people about raising temperatures in the room, and I've had people say, well, that's not going to happen until, you know, Joe dies or Joe retires or something like that. And there's been a lot of friction between IT and facilities. It was the topic of conversation at a lot of events for a number of years, and then the topic went quiet for a number of years, 3 or 4 years. I didn't hear much about it for a while. But then in the last couple of years, I'm hearing the topic come up again. And the conversation of how organizations are structured so that they can succeed at dealing with the issues that they're faced with, the increasing density, the pressure from regulations and pending regulations, the desire to, you know, increase the capacity of the sites and operate at the lowest possible cost. So there's a number of decisions that IT makes, that the IT side of the organization makes, that have a direct impact on facilities. And if those decisions are made in conjunction with the facility side of the house, then there's a much greater chance for success. And I'll even go so far as to say that it's close to impossible for a data center to operate as efficiently as possible and get as much capacity out of the site as possible without IT and facilities working closely together. So with all that said, I'm happy now to hand the conversation over to Ian, and he'll be going through a number of very detailed topics on how these decisions affect facilities and some nice examples. And I encourage you to take some notes. We will have a nice opportunity for question and answer at the end. And especially if you disagree with something we say, please take the opportunity to bring that up as well. So, Ian, it's all yours.
Okay, thank you, Lars. Good morning, everyone. Good afternoon to any folks on the east side of the country. Can we get the next slide, please? So we'll be looking at several decisions that our friends in the IT community make that have direct impact on the effectiveness and efficiency of the mechanical plant, on the risk of appearing to pile it on, but as a matter of fact, much of what's done on the IT side of the house does directly affect how things work on the mechanical side of the house. So we'll look first at decisions regarding the specifying, procuring, deploying of servers. And one of those decisions has to do with the delta T of those servers, which historically has been the difference between blade servers and flat servers. So that's changing a bit today. Those decisions have direct bearing on the operating expense and the acquisition costs associated with the mechanical plant of the data center. Next. And we look at those differences based on the fixed relationship between airflow and delta T. And delta T here we're talking about the amount of temperature rise of the cooling air as it moves through servers. That's a fixed relationship, and we see here in the chart where we have a low delta T, we have a pretty high airflow demand, and we have higher delta T, so we have a low airflow demand. And that difference ranging from 211 CFM per kilowatt down to 79 CFM per kilowatt is a pretty extreme variation. And if we look at the example on the next slide, it'll show how that actually plays out. So here we look at a typical pizza box server versus a typical blade server system, and the airflow requirements are required to serve the delta T's of those servers. Next. And so at a 0.5 megawatt example of the data center, we can see that our flat servers are consuming or requiring almost 75% more air than our blade systems. And that has a direct impact on both the operational cost and acquisition and capital costs per data center. Look at the next slide. The airflow requirement of 43% less airflow required by blade servers is not a linear cause for energy savings, but we actually take advantage of our fan affinity laws there, and we get a cube of that airflow savings translated into energy savings. The second bullet here kind of walks us through that math real simply as we look at if we're running our fans at 50% flow, we take 0.5 cubed, comes up to 0.125, so that translates to an 87.5% energy reduction, and so that's where the 81% energy savings in our example case study shows through. And the savings actually for the fan energy is also accompanied with a capital savings for those higher delta T servers. If we were looking at a high delta T data center, it would, for a half a megawatt, it could require 4 cooling units for an N+1 redundancy, and the flat server data center would require 7 cooling units for the same N+1 redundancy. So in addition to the fan savings, we would get about a 43% capital expenditure savings as well. Now, one thing to consider here is that historical differentiation between blade servers and pizza box servers is breaking down a little bit as some manufacturers are producing more efficient 2 and 3 unit servers. So your shopping for these servers should include delta T or kilowatt, CFM per kilowatt as some of your criteria. Also, when we're specifying servers, we're going to be specifying Class A1, Class A2, Class A3, or Class A4 servers. This becomes a little bit more complicated because you're very unlikely to find those labels on the boxes or on the nameplates or on the user documentation for those servers. So we're going to need to look at some other ways of identifying those. But these are important decisions because they will affect the operating temperatures that we're using in the data center, that will directly impact our access to free cooling hours, our chiller operating efficiency. They might even affect the capital investment on, are we even going to need to build a mechanical plant for the data center? And they can also affect what I call PUE anomalies. And this has to do with when we can reduce the PUE of a data center, but actually increase the overall energy consumption of the data center. This can happen if we're using Class A1 servers, for example, at 86 degrees. You're going to see somewhere around a 40% increase in air demand. That will translate, due to the fan affinity laws, which work against us as well as they work for us, to over 250% increase in fan energy, which could increase the total server energy of the data center by up to 25%. That increases our divisor of the PUE equation, so we get a better PUE, and we get a much higher total energy use. We can contrast that to A3 servers at 86 degrees, where we might see only a 3% energy increase, only 1/8 of the energy increase that we're seeing from A1 servers, which would be easily offset by all the savings we get from more free cooling, better chiller efficiency, from the other savings here. Warranty costs also bear into this, and real estate costs as well, because if we can avoid the mechanical plant and all the associated hardware and real estate required for that, that would realize those savings as well. So the specific classes we're looking at are on this ASHRAE chart in the far left-hand column. You see them in the middle of the page there, the A1, A2, A3, and A4. Like I said, you probably won't find these advertised by the server manufacturers, but what you will find is in their user documentation these operating temperature ranges. And so those are the temperature ranges that will produce those results that we talked about on the previous slide. Now, one thing that we need to ask ourselves while we're considering these server classes in these temperatures that may allow us to run our data center occasionally up into the 90-degree range or higher, what is that going to mean for the reliability of our computing equipment, and how long can we actually allow ourselves to wander into some of those higher temperatures and still meet our reliability and availability goals? Well, the answer to those questions come with the ASHRAE process, which they define as the X factor. This is based on starting with a baseline assumption for what kind of quality we would see from our servers, what failure rate, if we operated 24/7 all year with a server inlet temperature of 68 degrees. The 19 different OEMs that serve on the ASHRAE TC 9.9 IT subcommittee have compiled their failure reports, their user data, and also the onboard temperature reading capability that they have from their customers, and looked at failures at different temperatures, and they were able to come up with percentage of variations of improvement or poor performance at higher or lower temperatures from that 68-degree baseline. The premise here is that if we're doing free cooling, we would follow Mother Nature in the application of temperatures in the data center, and therefore we could bank during the winter months or cooler operating temperatures some favorable conditions that would then offset the higher operating temperatures during the warmer times of the year. So if we look at some examples here, the first one here comes from the ASHRAE white paper that introduced the X factor, and here they looked at Chicago and what would happen if we ran a data center with no air conditioning at all. And then we compared that to running a data center all year long at a 68-degree server inlet temperature. And what they found with the temperature profile in Chicago, that they came out with an X factor of 0.99. That means they would actually have a 1% less failure rate for a data center with no air conditioning versus the data center that ran all year long at 68 degrees. And then the next slide will show us how a similar methodology was applied to various cities around the country when they further talked about this when they released the 4th edition of the ASHRAE Environmental Guidelines Handbook. So you can see we've got some cities that were going to have lower failure rates of our servers if we ran the data center without any air conditioning. And then we have some cities where we have higher failure rates. But we just want to put that a little bit into perspective, and we can use Phoenix as an example for that, where if we ran a data center in Phoenix with A3 servers and we had no air conditioning, we would see a 20% increase in server failures. But let's say, for example, our true experience has been that we see maybe only 3 servers die on us in a year. So a 20% increase would actually only be 0.6. So it would take us 2 years to actually see an additional failure. And we may decide that's an acceptable risk if we can avoid the expense of building, deploying, and actually operating the mechanical plant. Furthermore, if our experience has been where we're seeing 75-degree inlet rather than the hypothetical baseline of 68-degree inlet, Then when we run this data center without any air conditioning, that's only a 7% increase in failure rate. So it's going to take us 4 or 5 years to actually see the one failure, which may extend beyond the cycle of our technology refreshes. So we may never actually see that failure. So this analysis needs to go into the procurement decisions on servers. Now, finally, to put one final bit of perspective on that, you really can't buy A1 servers anymore, and A2 servers are becoming harder to find. Your data centers today are probably full of A2 servers. Servers that you buy today are more than likely going to be A3 servers. So if we're looking at a premium cost decision, it's really going to only be between A3 and A4 servers today. Specifying equipment that breathes front to back is another decision that is important that the IT community makes. It has a direct impact on the operation mechanical plan of the data center. This will affect our hot aisle separation. It will affect the density potential of the data center. If we have a lot of equipment in this data center that breathes side to side, that return air contamination in the data center is going to drop to potential capacity or maximum density in that space. It's also going to result in more fan energy being used to compensate for that mixing of return air, and it's going to result in higher chiller plant costs and reduced access to free cooling because of the lower set points required to compensate for that mixing. And we may also be looking at the way we integrate some of these side breathing switches in the data center is to take on the cost of separate rooms in which those switches are deployed. Now, all standards, best practices, and we all know all of our equipment needs to be breathing from front to rear. However, we don't necessarily do that because there is equipment out there from some suppliers that does breathe side to side, does breathe front to top, does breathe side to front and side to rear, that has other advantages that we continue to use in these spaces. So what we need to figure out is how can we make all this equipment behave as if it were breathing front to rear as far as the rest of the data center is concerned. So we can look at an example, a case study that I actually worked on a few years ago on the next slide that kind of walks us through this. So we started with this data center, about a half a megawatt, and we had an entrance room, a point of presence here with open racks in a cage, and we see that we have inlet temperatures ranging from 73 to 90 degrees. And then out in the middle of the floor, we had a core switch and some storage cabinets that were breathing side to side and front to top, and we were getting 56 to 85 degree inlet temperatures. While those inlet temperatures were acceptable to the manufacturers, they were not acceptable to the SLAs that were agreed on with the customer here. And just to meet the performance in this data center, we had a 72 degree set point resulting in a 54 degree supply temperature, and we had airflow that was running over 21% in excess of the actual demands of the airflow in this data center. So on the next slide, we can see the modifications that we made to the space by taking that cage with the open racks and changing the cage to a strictly vertical cage going to the ceiling, and taking out the open racks and replacing them with chimney cabinets, and then replacing the side breathing and top breathing storage and core switch cabinets in the middle of the data center with containment that made the data center view that equipment as if it were breathing front to rear. And these changes resulted in higher supply temperature but lower inlet temperatures, resulting in 38% chiller plant energy savings and a reduction in airflow to nearly 34% fan energy savings. Next slide, please. Storage type. Everyone knows that we can't afford solid-state storage, but these decisions have an impact on the data center that may actually change that cost justification model. These decisions affect access to free cooling, total operating energy budget. They could affect whether we're going to buy, deploy, and operate a mechanical plant at all, as well as investment in humidity management. And this really has to do with strictly the requirements for rate of temperature change. And these are not absolute numbers here. For example, if we were looking at a 2-degree temperature change in 10 minutes, that exceeds the 9 degrees per hour rate of change, and so that would be unacceptable. And so we can see in many parts of the country, if we're doing free cooling in areas where we get rapidly moving weather fronts with pretty good temperature differences on the leading and trailing edges of those fronts, that we would not be able to accommodate these kinds of changes. So the decision and speccing process here needs to be to look at if we've done all the other things we've talked about up to this point in the presentation, and we've got the real solid kinds of airflow management that Lars will talk about at the end that allows us to take advantage of these things. Then does investing in tape store or solid state storage actually allow us to not build a mechanical plant and to save those capital expenses and operating expenses? Cooling unit set point is a facilities function that is typically driven by our friends in the IT community, and so we look at that as well, and its effect on chiller efficiency, on cooling unit efficiency, and its effective life as well. If we're just running a cooling unit on all the time at some low level versus cycling it on and off or cycling hot and cold, we get a lot more life out of that equipment. We're also looking at humidity management expenses, access to free cooling, and general operational discipline. If we're doing our responding to problems in the data center with hotspots or cooling issues by increasing airflow and reducing set point, we're masking those kinds of problems that the discipline of good airflow management that Lars will be talking about at the end of this would allow us to have access to all the other benefits we've talked about up to this point. So the the key thing here is data center cooling is not the same as comfort cooling, despite the common practice in many data centers around the world today. And by that I mean comfort cooling, where we have a thermostat with some set point, and whenever the return air exceeds that set point, we fire up the air conditioning to cool the whole space off, as opposed to the best practice for data center cooling, where we just create a set point that, with good airflow management, should only be maybe 2 or 3 degrees below the maximum IT inlet temperature in the data center. And that allows us then to get the access to the increased chiller efficiency and access to more free cooling hours that come with these decisions. And related to these set point decisions in a supply temperature, let's say set somewhere around 75 or 76 degrees or higher, versus a 70-degree return set point resulting in supply air in the low 50s. So if we have a condition with 50-degree air with 55 grains of moisture per pound of dry air, that equates to 100% relative humidity or rain, or very least condensation. And if we have any one of these set points in this list at the bottom of this slide with a 70-degree set point, for example, with 50% relative humidity, that's going to produce supply air that meets those conditions of 100% relative humidity. That's a problem either in terms of producing condensation in the data center or dramatically increasing our costs for humidity management in the data center. So finally, cages are often a business decision rather than an IT decision, but everybody in IT and facilities needs to live with those decisions. And cages that are compatible with airflow containment affect everything, all the variables that we've talked about up to this point. And the fact of the matter is that cages and containment do not have to be mutually exclusive, that there are various ways of integrating those two aspects of the data center. And the next slide will look at that case study that we looked at a little bit earlier in the presentation. And in that case study, we had our point of presence racks in a cage, and what we did was we modified the cage from going over the top of those racks to being vertical to the ceiling, and that allowed us to put in chimney cabinets, resulting in a 38% solar plant savings, and because of higher temperatures we were able to achieve in a nearly 34% fan energy savings, because we weren't having to compensate for all the hot air in the data center. So with that, I'll turn this over to Lars to talk about what is required in the data center to take advantage of all those decisions that I've just talked about.
Thank you very much, Ian. Yeah, as I mentioned earlier, the topic of IT and facilities kind of was out of the normal conversation for quite a while, and I also noticed that the topic of airflow management prerequisites or fundamentals, if you will, was out of the topic of conversation for a few years, but has been returning as well. And we're talking about very simple things that were all we talked about at the beginning of this airflow management awareness industry about 12, 15 years ago. You know, it was the topic was sealing cable openings in the raised floor helps manage the air, and it was an obvious concept, and it got a lot of consideration for a number of years, but then it fell off of a lot of people's radar after they made an effort to improve sealing of the raised floor or installing blanking panels. But very few people have finished the job and done it very thoroughly. And it's not a very exciting topic, but it has profound impacts. And as we said here on this bullet, this first bullet, everything is affected by these fundamental best practices. And the goal of airflow management is to create enough of a separation between the supply air and the return air that the total flow rate of conditioned air can be reduced as much as possible, and the temperature of that conditioned supply air can be increased as much as possible without negatively impacting the intake temperatures to the IT equipment. And these airflow management fundamentals are crucial for that. And if done well, there can be substantial fan energy savings, as Ian gave us that example, that just reducing the fan speed by 50% can produce over 80% savings in fan energy. We get benefits at the chiller, we get benefits at the cooling units, and we get the profound benefit of deferred capital expenditure, even leading up to adding up to the potential of deferring the build of a new data center. And you know, that's some real money when we're talking about deferring a multi-million-dollar project for a number of years. So let's talk about a few of these basics. Cable management. This often falls under the IT side of the house, their responsibility, or their employees are the ones running the cables. And there's a couple of places that this is really important. First is underneath the raised floor. One is just making sure that the installation of the cables presents the least possible obstruction to air movement under the raised floor. And so the best practice there is to mount them up close to the bottom of the tiles, but generally not in the cold aisle. If you put cable management in the cold aisle, then it's going to significantly impede the ability of the conditioned air to get out of the raised floor up through the supply tiles, as shown in this picture. And one other cable management issue that I didn't mention was that the cables at the back of the cabinet are also very important. If they're not managed well and kept off to the sides, then they can impede the exhaust air coming out of the servers, increasing the pressure in the back of the cabinet, causing the hot air to go out unintentional openings, either out towards the front of the cabinet, causing intake temperature problems, or out the bottom. We want to let that hot exhaust air coming out of the servers freely flow into the hot aisle. Then, as we have here on the slide, raised floor open area management is the next really important area to pay attention to. Very few people have quantified what percentage of openings in the raised floor are in a good location, and the only way that you have an opening in a good location is a supply tile in front of IT equipment. And all other openings, cable openings behind cabinets or perimeter penetrations, or as we see in these pictures, picture on the left, conduits running along the walls, every one of these openings is a bad opening. And all of them should be sealed. And it's surprising how much open area this represents when you go look at it and add it up. Then, of course, racks and managing the open area in the racks is crucial. Everyone knows that blanking panel is a good idea, but few people have implemented it really thoroughly. Another issue that comes up in managing open area in the racks is the design of the rack itself. And quite often facilities, people are aware of this problem of open racks, particularly racks that have space between the rail and the side of the cabinet, that hot air can flow around that opening through that space and into the IT equipment. But facilities doesn't have much control often over what cabinets are purchased. So this is another area where it's really valuable to have IT and facilities meet regularly and discuss airflow management, cooling efficiency, and all the related issues so that input can be given on cabinet design. We see here in this image that the bottom 2U in this cabinet and the left 2/3 of that equipment is receiving very high intake temperatures, and that's the result of just missing blanking panels in the bottom 2U, as well as openings between the rail and the side of the cabinet. And blanking panels, the ones that we've designed, are in our Hot Lock family line of products, and those installed in the space would block that airflow and solve the hotspot, the high intake temperature problems, with no other adjustments necessary. Then after the raised floor and the rack are managed, we're moving on to the row airflow management. There's a number of gaps here that need to be addressed, the gaps between cabinets, even if those are just an inch or two apart. And then, of course, we start to see problems where there's missing cabinets, either from just migration of equipment coming in and out of the room, or perhaps there's a building column in place preventing a full row of cabinets. So these openings need to be sealed so that the only way that air leaves the cold aisle is passing through the IT equipment. One of the areas that we see the most hotspots is at the ends of rows. And this can easily be solved by putting doors on the ends of the row, either the hot or the cold aisle, depending on which direction you're headed towards containment. And I often tell people that you get a lot of bang for your buck just by putting on doors and not having to go all the way to full containment. So here are a few of the other products that we've developed to manage airflow at the row level. We have the adjustable rack gap panel. That's an adjustable panel anywhere from like 6 inches to 60 inches to fill the spaces between cabinets. And then we've developed baffles for both cold and hot aisle applications that prevent air wrapping over the tops of the cabinets. It's not full containment, it's modular or partial containment, and it creates enough of a blockage that the supply air can be balanced with the demand air of the IT equipment without getting into all the hassles of fire suppression issues that you deal with when you put a full roof on top of the cabinet. And then I want to leave you with one last concept, which is, what is the approach to take when addressing airflow management? We've developed this protocol, which is the 4 R's of airflow management, and it reminds us to take a look at these 3 areas of airflow management: the rack, the row, and the raised floor. And one of the great misconceptions in the industry about airflow management is that I can install airflow management products and I'll see immediate efficiency gains. I'll see cost reductions. I'll see stranded capacity recovered. Well, that's not true in most cases. You might eliminate some hot spots and get some immediate benefits that way, but it requires making adjustments to the controls at the room level, the center of the circle here, to really realize those benefits. Once, say, a rigorous process has been undertaken to seal the raised floor, it's quite likely that it's possible to look at the room level and adjust either the fan speeds or the number of cooling units running to be able to realize those benefits of improving the airflow management in the room. So we've developed a video that goes into a little more detail about this, and happy to talk to you about this concept as well. So just to wrap it up, I'll hand it back to Nick, and then we'll get into your questions and answers.
Thank you, Lars. Before I wrap this up, I'd like to encourage you all to start submitting your questions now. If you look at the GoToWebinar Management adapter on your right-hand side, there's a place to submit questions. So please go ahead, type in your questions there, and we will start answering them very shortly here. I'd like also to take a moment to let you know of our upcoming and final webinar for Airflow Management Awareness Month. Next week, Lars will be talking about the 4 delta T's of airflow management. It's a very interesting topic because there are 2 less discussed delta T's that are pretty important and can have an impact on airflow management. So I highly encourage you to tune in for that as well. Thank you so much for joining us today. If you have any follow-up questions, here are the speakers' email addresses to contact them directly. I also encourage you to connect with Upsite. We publish content weekly on airflow management topics. If you can follow our blog there at blog.upsite.com. Also, we're very active on social media, specifically Twitter and Facebook, regularly posting related content as well. So I encourage you to follow us through those channels as well. So at this point, we're going to go ahead and take a look at what questions we have and start going through those. And it looks like we have a couple already in. So let's see here.
So the first question relates to asking about our opinion about cable management arms. It seems that they block exhaust from the equipment. Ian, would you like to comment on that? Ian might be on mute. Yeah, there's an upside to that, and there's a downside to that.
Okay, Lars, I'm here. I'm sorry, I was on mute.
No worries.
There'd actually been some research done some number of years ago by Dell, and they had published a couple papers on this where they looked at the cumulative pressure drop effect of those articulating cable management arms and how they consolidated cable often in the path of the server fan exhaust and the effect on the operation of those servers. Our recommendation has always been to not use those, and there's several things that well, a good example is with your power cords. I've always suggested folks should use the shortest possible power cord they can and leave one long power cord in your technician's toolbox, so that anytime you actually need to pull a server out on the slide where it's still powered, which typically you're not going to service while it's powered anyway, but if you have to do that, then take advantage of your dual power. Hook up one of your power sources to the long cable, disconnect the rest of your cables, pull that out, do what you need to do, put it back in, and replace your short cables and put the long cable back in the toolbox. But those cable management arms can be problematic, particularly for 1- and 2-use servers.
Right, yeah, especially when the cabinet is fully populated with those. What I see a lot of people going to is getting all the cable management, getting all the cables routed over to the sides of the cabinet as quickly as possible. And some people using wider cabinets, particularly if it's full of the 1-use servers and therefore that many more cords. John, you also asked another question about your racks having no side panels, and you mentioned that they were bolted together. So that's a great question. I get that fairly often, and it relates to a similar question, which is, do I need blanking panels at the back of my cabinet also? And you certainly don't need blanking panels at the back of the cabinet, and having the side panels removed from your cabinets, it doesn't have to be a problem. It's generally not a problem as long as the front face of those cabinets is sealed. If that vertical plane across the face of the IT equipment intakes is sealed, then having the sides off the cabinets is not a problem. The air is not going to really flow from side to side. It's all going to want to get out the back and head back towards the cooling units. Any other thoughts on that, Ian?
No, I mean, that's as long as the side panels are not integral to whatever that cabinet manufacturer is using to seal the front of the cabinet from the rear of the cabinet, then the side panels are really not needed for airflow management.
Yeah.
I actually have a question for both of you. Something I've heard from people at events is some people are afraid to increase their temperatures, or they get resistance to increase their temperatures because they have a lot of legacy servers and IT equipment that they're told requires colder air. In your opinion, is this true?
Well, if you've got a data center populated with older equipment, it's typically going to fall into that A1 category, which is still going to allow temperatures to get up to 90 degrees without there being a warranty problem for that equipment. Now, the flip side of that is that for that legacy equipment running with the warm air, it deals with that by ramping the fans up to a real high rate of speed to lower the delta T. So in fact, you for that older equipment, you may not be realizing all the economic benefits you might be expecting because the total server energy is actually going to increase to compensate for the higher inlet temperature.
Okay.
Yeah, this is Lars, and I've had a number of people push back on that concept as well. However, the point at which the returns start to diminish by raising temperatures is generally higher than most people realize, or certainly higher than most people are operating at. Yeah, it has to do with that class of server. But generally, it's with the intake temperatures, the average intake temperatures, and ideally consistent intake temperatures being somewhere in the high 70s. And it's still very uncommon for data centers to be operating with IT equipment intake temperatures consistently, and evenly in the high 70s. There's usually quite a bit of room to go.
Okay, thank you for that. Okay, seems like we don't have any additional questions at this time, so I think we can go ahead and wrap this up. If you think of additional questions, you've got our contact information on the screen there, so feel free to contact either the speakers directly or connect with Upsite, and we will answer the questions for you. Thank you again for attending our webinar, and we hope to see you next week as well. Also want to let you know that a recording of today's presentation will be made available, as well as the slides, and those will be sent to you by the end of this week. So thank you again. Bye-bye.